Next up is logarithmic functions. And to start off by thinking about what is a logarithmic function, what is its purpose to math, I think it's most helpful to remember that a logarithmic function is purely the inverse of an exponential function, like what we've been talking about in the previous chapter. And that's basically why they exist. If we look at the definition, which is found in an average textbook, it would say let a be a positive number with a is not equal to 1. The logarithmic function with base a, denoted by log with the subscript a beneath it, which is kind of hard to see probably, if you're looking at what I have, is defined by log base a x equal y, arrow thing ay equal x. And so before we kind of talk about what that means, what I wanted you to notice is on the right-hand side over here, it says a to the y is equal to x. So what we have is a simple exponential relationship where y is kind of the input in the exponential expression, x is the output. And if we look at the way that log base a of x is defined, this arrow is called the if and only if arrow in math, which is just a way of saying that if this is true, then this must also be true and vice versa. But basically, if one is true, the other is also going to be true. If one is false, the other is also going to be false as well. Basically an equivalency statement between these two expressions. And basically what it's saying is that an exponential equation can be rewritten as a logarithmic expression or equation where, notice that x and y, the positions have been changed. Where log base a is equivalent to, with the input in log base a of x equal y, is the same as a to the y equal x. Or basically, again, kind of as a way of saying, well, if I switch the locations of x and y, and remember, that's really the key with an inverse function, right? In an inverse function, we swap x and y in order to solve the inverse. That's basically what this is getting at. And let me just throw an example. Like you can plug whatever numbers you want into here, and it should make sense. So like if we were to start with an exponential, let's just make up a random one. Let's just say 2 to the third power and of course 2 to the third power is equal to 8. And basically, so this would be, in this situation, a is going to be my base, 2, 3 is y, and x, I'm just picking to be 8. Well, of course, if 2 to the third must be 8, it can't be anything else. So how would we rewrite this as a logarithm? Well, basically, again, this is a way of saying, well, if I were to write this as log base a, where 2 is, again, that's how you can remember the base of a logarithm, is it's going to be the same as the base of the respective exponential function. A, again, written consistently for both cases, but what swaps is x and y. So basically, this is the location of y. This would go on the other side of the equal sign, and the 8 would go in here. And basically, this would be our equivalent logarithmic equation, and this would also be true. And basically, that's kind of a confusing way to define a function. But again, as I was saying, the key thing here is it's the inverse to an exponential function. Because usually, we think about 2 to the x power, we have like our domain and range. Within a logarithmic function, the range, the input is going to be the exponential expression. And what we're going to get out from that is going to be, well, what was the respective input? And like, what if this is getting a little confusing? I feel like I'm not doing a very good job of explaining this right now. It says, so log base a is the exponent to which the base a must be raised to give x. And what I recommend is to think about evaluating this. How a logarithm will work is we're going to try to figure out, well, what power do I need to raise this to get to this in sort of that way. So let's practice a few more. Let's practice a few logarithms and try to figure them out without using a calculator. And of course you can use a calculator, and I'll show you how to do that shortly. But let's say we wanted to know, what is log base 10 of 1000? So again, what I would start to do, this is just how I solve logarithms in my head, is I think about, well, what power would I need to get from 10 to 1000? It's sort of like a root, but it's not. And that's exactly what a logarithm is. It's basically trying to connect the dots, figure out what power. And how you can remember it is the one on the bottom is always the base, because it's the small number, I'm trying to figure out what to raise it to. And if you're wondering, well, why is it log? It's a shorthand for logarithm, which is just the word which is expressing for trying to figure out the exponential expression. And basically, well, in this case, it'd be 3, right? Because 10 times 10 is 100, and times another 10 is 1,000. So I would need 3 tens to get to 1,000, and that's exactly what a logarithm will tell me. It tells me what exponent I need to get from point the base to the input. And again, you can always translate a logarithm. This is kind of a different way of doing it. Because like, again, that's how I would do it. Like in looking at the next one, I would think, well, 2 to what power makes 32? 2, 4, 8, 16, 32. That would be 5 2s. And so you can kind of like repeatedly figure out how many multiples I need to get to there. Or like 5, I need 2 5s to multiply to get 25. And those ones are pretty straightforward. But like another way of doing it, this is how a lot of teachers that I've seen will teach it. They'll say, well, if you're trying to solve a logarithm, you can always just use the definition, which is basically a way of saying, well, a is the base, the other side is what I don't know, and basically 1,000 will switch to the other side. And so what I would then need to solve is 10 to what power is 1,000. I mean, that's exactly what I'm saying to do in your head, if you see what I mean. But that's, what this logarithm will figure out. Or like in the second case, it would be 2 to what power would get me 32. And the answer would go on the other side. And so in essence, basically a logarithm will help me solve an exponential equation. That is the purpose. And again, it's an inverse because we're swapping the input and output in the exponential function, right? Like if I switch these around, what I would equivalently write is 2 to the 5th power is 32. And it would be, the same as an exponential function, but I'm just changing what is inside and outside. So it's very much like a square and a square root. The square root undoes a square. A logarithm undoes an exponential with a particular base. So looking at a couple more, like let's look at the two on the right. Now there's a couple basic properties of logs of any base, and that's that if the base matches the input, this will always give me 1, because 7 to the first power always keeps it consistent, right? Because 1 7 makes 7 in any case. And another one that's consistent for logs of any base is if I take any logarithm of 1, well, the answer is always 0, because again, in the same way, I think about, well, 7 to what power makes 1, and the only way to make 1 when exponentiating, and that's just a verb for raising something to a power, is to take it to the 0 power, right? Because anything to the 0 power is always 1. And so, below where I say there's properties for logs of any base, log of anything of 1 is always going to be 0. And log base a of a, if those two numbers match, will always make 1. And there's sort of like the basic canceling properties of logarithms. Now let's look at a couple trickier ones, kind of like, well, what happens if I have fractions or negatives or decimals or whatever? Like, say I wanted to know, well, 3, what power do I raise that to get to 1 over 27? But when I'm seeing a reciprocal, again, I could write it like this, if that helps you understand a little bit better. Well, in order to get a fraction, to change exponents in division, we know that needs to be a negative exponent, because a negative exponent will flip it over. And then from there, I would just want to figure out, well, how many 3's are in 27? 3, 9, 27, that should be 3 3's. So this should make -3, because 3 to the -3 would, again, reciprocate and leave me with 1 over 27. But also, if you're not great with your exponents and stuff, again, you can always go to your calculator, and I wanted to show you where logarithms are. If you go onto the main button, you'll notice that there's the log function right here, but this is always the common log base 10. If you want to access log of any base, you need to go into your math menu, and if you scroll down a ways, you should have a log base function in there. Now, some of these calculators don't always have it programmed in there, and if your calculator doesn't have it, I'll show you. We'll learn another way to do it in the next couple videos. So don't sweat it for now. We'll revisit this issue. But basically, you could do log base 3. You type the base in there, and then 1 over 27 right there. And that would leave me with -3. So, if you're not great with exponents and figuring this sort of thing out, you can always just use your calculator. And, similarly, if I was to look at the next one, I would think 10 to what power is 0.01. Now, to find a decimal, it might be helpful to write that decimal as a fraction. And remembering that 1/100th is actually just literally 1 over 100, that's another way that could help. And again, since it's a fraction, that would be to the -2 power. But as I mentioned, you can always use the common log, which is the button right there, to figure out log base 10, you know, if you wanted to do it that way instead. And then let me create a little line there to separate my work from my answer. And then also, say for example, I was trying to figure out, well, what's log base 36 of 6? Because again, the base always is the base of the exponential expression. And I'm always trying to figure out, well, what do I take this to get here? A common mistake might be to say 2 here, but that would be if the numbers were switched. I would have 6 squared as 36. But in the same way, the answer would actually be the exact reciprocal of that 1/2. Because if I take 36 to the 1/2 power, that's equivalent to the square root of 36, which would be 6. And remember, it's not a multiplication thing, it's always an exponent thing, which can be confusing, and you got to make sure to think like, well, what does a fractional exponent mean? It means a square root. What does a negative exponent mean? It means a fraction, and so on. Anyways, there's a couple other properties of logs of any base which I wanted to mention. The first of which is called the cancellation property. This is a very important property, which is actually relating back to our what we call the inverse function property back in chapter 2. And if you recall, what the essence of that property was, if I plug in, if I compose f and f inverse, what that always does is produce x. And same with if I compose f inverse with f of x, they always produce x. Oops, you can't see what I'm writing. There we go. And this was called the inverse function property back from 2.7. And the essence of that property was, because if a function and the inverse are applied consecutively, well, inverse functions always undo the original, and what happens is they'll cancel each other out, kind of like plus or minus, or times 3 and divide by 3. And vice versa, whichever way I compose them in, they will always perfectly cancel and leave me with simply x, the input. And basically that's exactly what the property for when I stick a logarithm and an exponential together. Because as I mentioned at the beginning of the video, really this is just a way of saying that a logarithm is the inverse to an exponential. And if I were to stack them together, they're going to cancel. So let's say we wanted to know what's the log base a of a to the x. Well, again, I could think about this based on the definition of the logarithm. I'd want to know, well, what power would I need to raise a to get to ax, right? Because that's how I can change an exponential to an equation to get the input. And the obvious answer here is, well, I would need to take a and raise it to the x power to get ax. That's the obvious only solution to this unknown. And basically what will happen is log a and base a will cancel each other out. And basically if I were to write it like this, it's kind of like if I took log base 2 of 2. And this is another way that I remember, you know, my teacher teaching me in high school, is that if the numbers match, it's always going to be 1. And that's kind of what's going on here. If I have log base a of a, those numbers match, and what happens is I get 1. But actually what also happens is the x is no longer in the exponent, it just leaves me with x. That's one thing I remember wondering in high school. I didn't really get exactly that. But basically it leaves you with just x all by itself, no longer in the exponent, because really that's the answer to the logarithm. It's what power I need to raise a to get to ax, obviously just going to be x. And very similarly, if I have the opposite thing, a to the log base a of x also cancels in the same way due to composition. Basically a and log a will additionally cancel each other out. And if you're wondering, well, why? Well, you could always use this property in reverse. If you have an exponential, you could always rewrite it as a log, because both definitions are the same. So if I have, basically this is going to be my y, and my other side is going to be x. So what I would do is I would swap them. I would have a to the what is equal to log base a, and I would need to put a logarithm in front as well. Sorry. Let me try to be very clear about what I'm saying. Basically, I'm going to take these 3 things and plug them in over here, because these 2 things must always be equivalent. So x is basically, this exponential will become log base a, and the base of my expression right here is a. The input will be the other side, which is unknown, and the right hand side will be my exponent, which is the entire, which would be the y in that scenario. which is of course just the little y there on the other side. So it's kind of like I'm moving this here, I'm moving this here, and I'm putting a logarithm in front. But basically, again, it's a very similar situation where the only answer to this would be x, because that, and again, the simple reason why is because when I put them in succession, when I compose a function in their inverse, they always must cancel each other out. And that's why knowing that logarithms and exponentials of the same base a, if you know their inverses, you just know that that's going to happen. And that's, you know, a very important property of inverse functions. And again, well, why do we care about all this? It's very helpful for solving equations. And, you know, as I mentioned earlier, log base 10 is the common log. So if you ever see log without a base, and this is something where, you know, you're always going to have a little number there. But if there's not one, you can always pretend there's a 10 in there. Like you could write a 10 in, but basically a log when there is no base represented is always base 10. And so, you know, again, if you use this log right here in your calculator to say find what's the log of 10 million, well, that's going to be 7. But, you know, this kind of helps us see what a logarithm function does. A common log basically extracts the numerosity or the size of the number from it. Because, like, you know, when I have 10 million, it basically will count the number of zeros, because 10 million is consisted of 10 times 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 10. I don't know if I just said the right amount of tens, but I think you see my point. But it will return how many digits it has in it. And that's what the common log, and that's why it's common. Because, you know, our whole numerical system is based on tens. And, you know, that's the functionality behind common log. Or say you wanted to do a log of 0.1. That would be -1, because 0.1 is 1/10, which is 10 to the minus 1 power. So in the next video, I'll talk a little bit more about the natural log, and we'll look at, well, what does the graph of a logarithm look like?